All right, this is 4.4 Math 31 Part 2, where we're going to be looking at just a couple basically harder situations with optimization. Right away, I think it really does help to have a diagram or something that you can kind of attach a visual to it. And there's a lot of different ways to do that. I'm going to show you a lot of this stuff in Desmo, so I'll just pull that up. That blue graph is 6 minus x squared, and then the point 0, 3 is right there. What we are trying to do is trying to find the shortest distance from this point to the curve. And most students can kind of eyeball it as right here and right here. Those look like the shortest dotted lines I could kind of draw to that. But we're going to do this in a really algebraic way because it eliminates, really guesswork. There'd be no way to do that accurately without the calculus. This is going to be my 6 minus x squared. Sorry, it's not in blue. And then my point is 0, 3. I'm going to eyeball is right about here. Now, really important that if I do connect that point, I'll put 0, 3 beside it. This point on the curve, it's an unknown point, so we can label it as x, y, but everywhere on that parabola, y is equal to 6 minus x squared. So we really could call this point x, 6 minus x squared. Now, the reason that's such a big advantage, and it's something that you haven't done a lot, but the distance between any 2 points is the square root, and it's really similar to the slope formula, x2 minus x1 squared plus y2 minus y1 squared. If you get a chance, you can Google that or see where it comes from. It's just an application of the Pythagorean theorem. Really, really useful to talk about the distances between any 2 points. And we'll actually see it kind of in the future in a few different examples as well. Now, what's really, maybe not unique about this, is that this d is minimized, which is what we're looking to do in this question, when d squared is minimized. And the reason why that's so important is that it does allow us to, instead of dealing with a pretty ugly formula within a square root and so on, that what we're going to deal with instead is d squared is equal to, and then we can just write x2 minus x1 squared plus y2 minus y1 squared. And that does make life a lot easier. What we have to do for, x2 and y1, I'm just going to put 0.1 over here, and I'm going to make 0.1 just to make it as positive as possible. That's going to be the point on the curve. So x, 6 minus x squared. Now, importantly, that means that x is x1, and 6 minus x squared is x2. X2, sorry about that, that's Y1. And then if we look at the point 2, which is going to be the given point, 0, 3, I won't mess it up that time, this is going to be X2, Y2. Now what I'm going to do is I'm going to take that information right here, and I'm going to plug it into my distance formula. And I get the distance squared between these points is going to be 0 minus x squared plus 3 minus, in a bracket, 6 minus x squared. Now, this is now a function in 2 variables. We have the distance squared between the points, and then we have some ugly expression. Now, to make this a little bit simpler, I'm actually just going to write this as capital D of x, because that quantity is what we're looking to minimize. And then expanding this, I'll do it in 2 steps here. Negative x squared is x squared, plus this becomes 3 minus 6 is negative 3, but then there's a positive x squared there. So it's x squared minus 3 squared. You could certainly take the derivative of this point, and it's actually not that bad of an idea, but most students are more comfortable expanding the x squared minus 3. So I get d of x is equal to x squared plus, all right, x squared times x squared is x to the power of 4. Then we'll have minus 6x squared, and then we'll have plus 9. So the formula, or the function, I should say, that we're looking to minimize in this case is x to the power of 4 minus 5x squared plus 9. Now, with your knowledge of polynomials from Math 30-1, you should know that because that's a quartic with a positive leading coefficient, that will indeed have a minimum. All right, from here, we are going to take the derivative. So I'm going to find d prime of x, which is 4x cubed minus 10x. And then I'm going to set d prime of x equal to 0 and solve. So if 0 is equal to 4x cubed minus 10x, we can say that 0 is equal to x times, all right, we have 4x squared minus 10. This is up to you whether you manipulate it like this or not. There's a couple different ways of doing this, but we're going to get a few critical numbers. We're going to get that x is equal to 0, but we're also going to have when 4x squared minus 10 is equal to 0. That means that 4x squared is equal to 10. X squared is therefore equal to 10 fourths. So x is going to be equal to the positive negative root, and 10/4 reduces into 5/2. We have three critical numbers. Now, what I'm going to do to talk about that first derivative test and so on is I am going to show you the distance function. So this red function in Desmos is the distance between these points. And we can see that they're quite far away as x is negative, and then we hit the minimum distance of 2.75, but then the distance goes back up. And when x is equal to 0, the distance between these points is 9. Now, it's a tricky idea that when we talk about putting that function in, really what we want to do, and I should apologize, this is actually d squared, not d. The minimum values of this distance occur at these 2 points, negative 1.581 and 1.581. Guess what that number is? That is the square root of 2.5, or 5/2. Now, using that graphical knowledge as well is pretty important, because that's really our first derivative test, and we could do that through the sign chart in a lot of different ways, but we know that, and when x is equal to positive or negative square root of 5/2, capital D of x is a minimum. That means the distance is a minimum as well, so those points work out to be root 5/2, 3.5, and negative root 5/2, 3.5. Now, it should be noted that both of these points are on the graph of y equals 6 minus x squared. Very, very important to remember what we've actually solved for, and those points on our parabola give us the shortest distance to 0, 3, which might be useful if you're looking to redirect a plane, or build a bypass onto a ring road or something like that. You want to use the least amount of concrete possible, so you want to minimize that distance.